Swayam Prabha. Digital India. Educated India.
Now, delta Q equal to C times delta V naught, which is half, we wrote T by 2 and delta IL by 2. Right? And delta IL by 2, if I try to write it in terms of whatever I have written for V naught, again, so I have written delta IL equal to V naught multiplied by T off divided by L. So let me write that again. So this is half T by 2 and I can write V naught multiplied by T off. So 1 minus D times T, 1 minus D times T divided by 2L. Okay? So I can write this as 1 by 8 F square, that is switching frequency. SW is switching frequency square, and L of course, and I am having V naught multiplied by 1 minus T. Right? Okay? So this is going to be C times delta V naught by V naught. I am bringing in this V naught here because that is the voltage ripple allowed. Right? Or that is the voltage ripple which I am going to calculate ultimately. So this is 1 minus D divided by 8 F SW whole square multiplied by L. From which I should be able to calculate what is the capacitance value given my inductance value already, switching frequency already, and whatever is the voltage ripple that is allowed. If I am given this is the voltage ripple that is allowed, then I should be able to definitely calculate this. Right? So this gives me a way for, designing the capacitance for a particular voltage ripple. Of course, given switching frequency and inductance values, and of course the operating condition, because duty ratio also I have taken into consideration. So the operating condition is given already. You operate it at this particular duty ratio. That is also given. Right? So is this clear? Okay? One more thing maybe which we would like to look at is, here I have taken T on to be much smaller as compared to T off. If T on is also 50% and T off is also 50%, let's say, in that case I am giving ample time for the current to rise and ample time for the current to fall. Look at it qualitatively. Basically, if I give 50% time for the current to rise and 50% time for the current to fall, I am giving maximum amount of duration that can be given for rise and fall. Both are equal. If I don't give sufficient time for the current to rise, that is T on is much smaller, then I am limiting how much could be the rise in the current. On the other hand, if I make the T off to be much smaller, then I am limiting how much current can fall really. So when I give equal amount of duration for the current to rise and fall, I am maximizing the possibility of having a very large delta IL value. Right? So normally the current ripple is maximum when the duty ratio is 0.5. That is actually the worst condition of current ripple. This can be proven if you try to take probably one of these expressions, either delta IL equal to V naught multiplied by T off by L, or if you try to write V in minus V naught equal to L delta IL by T on. So there also you have an expression for delta IL. So when will delta IL be maximum? V naught can be written as V in multiplied by D. You can write that as V in multiplied by D. So I should be able to write this as, for example, delta IL equal to V D times V in multiplied by 1 minus D times T divided by L. Right? I have just written this V naught multiplied by T of. V naught is D times Vn. T of is 1 minus D times T divided by L. That is what is delta IL. When will delta IL be maximum for this? With respect to D, you have to differentiate. Capital D, you have to differentiate. You will get 2D equal to 1, which is D equal to 0.5. Obviously, right? L is a constant. I'm not changing V in, I'm not changing L. Only thing I am trying to check is what happens to D. If I vary D, at what point I'm going to get maximum delta IL. So I'll get 2D minus 1 equal to 0. So D will be equal to 0.5. So this is one more thing you guys should realize, that when D equal to 0.5 for a given V in FSW, L, C, etc., I'm going to have maximum current ripple. I'm going to have really maximum current ripple. So D equal to 0.5 is the worst case scenario if I want to make sure that I have to design some particular circuit for the critical conduction mode, because under that condition, if it doesn't touch down 0, then I know for sure that it will not touch 0 at any point in time, normally. Right? So this is the worst case scenario. So much so for the buck converter under continuous conduction mode. What I have seen is only inductance current is either continuous or it is going to touch just the 0 value. It is not going to really dwell on 0 for longer, because if it dwells on 0 for longer, by chance if it is going to dwell on 0 for longer, what I have taken as this, the volt second area, what I have taken, this equal to this, that will not be valid, because the current would come down to 0, the inductance is dead for some time. And the load current is never going to be at a non-zero value at that point in time. So all these expressions, whatever we have derived, are valid only in continuous conduction region. When I have continuous conduction through the inductance, only in that region this particular thing is valid. Otherwise it will not be valid. So whatever we have drawn as the waveforms are all in steady state. Obviously, inductance current cannot start from a non-zero value. Not at all. Right? What we have drawn is all in steady state. I have been running this particular circuit for ages. That's all the more reason you guys should simulate and you guys should see first few cycles how it is really, the current waveforms and so on and so forth. They will be definitely not steady state. Initially for some time you would see that it is, kind of I minimum and I maximum are not the same for consecutive cycles. They'll all change, because the inductance is still trying to come to steady state after going through some transients. That's the reason. Right? Let's probably try to do one problem for buck. I'm not going to repeat this probably for every converter. Right? Okay. So this is essentially V in is 48 volts. V out, what we want is 16 volts. I have just arbitrarily taken values. Load resistance, I'm going to take 10 ohm. Capacitance voltage ripple has to be less than 1%. Right? That is 0.16 volt. should be less than 1%. Of course, we are talking about the output, obviously, because the capacitance is in the output side. And switching frequency, I'm taking as 25 kilohertz. Right? Calculate L critical for this condition. Okay? Generally, if we derive the L critical value, when we actually implement it in hardware, because of some variations that could happen in the construction of inductance and so on, and tolerance in components, we tend to take it as 2 times, 3 times the critical inductance to ensure that we will get continuous conduction mode for all conditions of operation. Right? So, if L chosen is, let us say, 2 times L critical, right? Calculate IL minimum, IL maximum, and let's say capacitance for this operating condition. Right? So, let us try to work this out. First of all, you can definitely calculate what is the duty ratio, because V naught equal to D times V in. So, this is 16 divided by 48. So, D is 0.333, 1/3. Right? So, once I have this, and if I have switching frequency, I can definitely calculate what is L critical, because I have got R value also. Let's look at the expression. L critical is this, 1 minus D multiplied by R divided by 2 FSW. Right? So, 1 minus D multiplied by R divided by 2 switching frequency is L critical. So, this is 0.667 whatever, multiplied by resistance is 10 divided by 2 multiplied by 25 into 10 power 3. So, this is 1.3 into 10 power minus 4 Henry, right, or 130, yeah, 130 microhenry, right, 130 microhenry. So, you can do a little bit of checking up. If you increase the switching frequency obviously to 50 kilohertz, you are going to have much lower, right, half of this. So, as you increase the switching frequency, the inductance value comes down further and further for the same operating condition. Let's assume twice this value as the L value. So, I am going to have L value to be, let us say, 260 microhenry. Okay? So, you should be able to calculate, first of all, say capacitance value, which we have again written the expression, delta V naught by V naught equal to 1 minus D. Okay, let me write this. So, I can write delta V naught by V naught multiplied by C equal to 1 by 8. I remember S, FW, S square. One more. What is the up? 1 minus D by L. Okay. So, 1 minus D divided by L. Right? So, delta V naught by V naught is given to be 1%. So, I should say C multiplied by 0.01 equal to 1 by 8 0.667 divided by 25 into 10 power 3 whole square and L, which is 260 into 10 power minus 6. So this is 625 multiplied by 260 multiplied by 8. 0.667 divided by that. How much is it? 5.128 into 10 power minus 5, which is 51.28 microfarad. Right? Anyway, you can check it up. So this is the kind of capacitance value we are getting. Again, we may put a slight factor of safety, or you might like to round it off, because when we make the design, generally we will not get 51.28 microfarad from the market. It's not possible. Whatever is the closest value, but a little higher value, because we need to adhere to delta V naught by V naught. We don't want to violate that. That is important. So that is the reason why we will choose something closer to this, whatever is available in the market, not 47 microfarad, which will be definitely available in the market. So whatever is the next available value, we will try to choose it. That's what we will do. How will you calculate IL max and IL minimum? We have the expression already, right? Delta IL you can definitely calculate, and you know what is the average value, right? So delta IL, once you calculate, delta IL by 2 plus I naught average. That is IL average is I naught. So I naught is 16 divided by 10, 1.6 ampere. So 1.6 ampere plus delta IL by 2 will be I max, and 1.6 ampere minus delta IL by 2 will be your I minimum. Right? As simple as that. So you guys should be able to calculate IL max and IL minimum. Right? So delta IL can be calculated as, what did we say? L di by dt. So V naught multiplied by T off divided by L. L value we have chosen, V naught we know, T off we know, because 0.667 multiplied by 1 by 25 into 10 power 3. So once we have delta IL, we can always write delta IL divided by 2 plus I naught average, which is 1.6 ampere, equal to I max, and I naught minus delta IL divided by 2 equal to I minimum. I cannot have I minimum less than 0. If in a problem, if you get I minimum less than 0, that means you have gone into discontinuous conduction mode. It is not continuous conduction mode anymore. That's what it means. For some kind of design values, if you are getting I minimum to be less than 0, DC-DC converter cannot have current in the reverse direction. Please understand that. So if I am getting less than 0, that means I have entered into discontinuous conduction mode of current. I have still not ventured into discontinuous conduction mode. What I am thinking is, I'll first complete the continuous conduction mode for all the 3 DC-DC converters. Then I'll venture into discontinuous conduction mode, just like what Daniel Hart has done, the same way. Okay? So now please use these values. Try to simulate your buck converter and see the waveforms of different components, voltages and currents.